Hey there, physical science students. This is Miss Ruark. We're in podcast 3.6, still in the energy chapter, and we're talking about waves, or energy unit, excuse me. We're talking about waves, so we're in chapter 15. All right, so let's get started. Also, I've noticed a little thing about your notes that you'll have to fix, so when we get to that point, just pay attention. All right, so before we get started, think about it. Imagine if you throw a rock into a pond or lake. What's going to happen when that rock hits the surface of the water? Okay, think about it in your brain. Okay, here's another one. When you're surfing, or when a person is surfing, a person moves just ahead of the wave. Well, where does the energy come from that moves the surfer through the water? And then what happens to a string on a guitar or another stringed instrument when it's plucked? Okay, all things to think about while we're doing this unit or this chapter. All right, so what is a wave? A wave is a disturbance that carries energy through matter or space. Okay, medium, we've already had this as a definition. Okay, it's when it's the matter through which the energy or the wave will travel. Okay, so if it's a sound wave, it's typically through air. If it's a ripple in a pond, it's through water. Okay, and the waves are going to carry that energy. So think about that surfer. That surfer is riding on the wave because that energy from the wave is pushing the surfer. So the bigger the wave, the bigger or the more energy there is. Okay, bigger wave equals more energy. All right, so mechanical wave. Mechanical wave, there's two different types of waves that we can talk about in terms of the wave. Well, there's wave types. Let's talk about mechanical versus electromagnetic. So mechanical wave is one that needs a medium to carry the energy. It needs the medium. It has to have a medium to transfer that energy. Okay, so sound waves, ocean waves, and seismic waves. Right? Well, we also have electromagnetic waves, which do not or does not require or need, that's need, a medium to carry the energy. So light, heat, and radio waves are all examples of electromagnetic waves. All right, so this is where your notes are all messed up. It says what causes most waves, and then it recopied everything from that previous part. So you're going to have to copy all this down. All right, what causes most waves? So a vibration is what causes most waves, and it's a disturbance in the medium. Okay, it's a disturbance in the medium. Okay, so vocal cords would be an example of a vibration because your vocal cords are vibrating together to produce the sounds, and this gives us sound waves. Okay, charged particles are what, those charged particles, they've got a lot of charge. They're unstable, they're bouncing, they're vibrating. Okay, and that produces your electromagnetic waves. Electromagnetic waves. Okay, and if I'm going too fast, make sure that you pause it so that you can get all this. All right, so the vibration is going to be passed on to the next or adjacent particles. Okay, so the one particle is going crazy. He looks over at his neighbor, touches his neighbor. Now the neighbor is getting that energy or that vibration passed on to him, and so that's how the energy is transferred. Okay, and then there's two types of waves that we can talk about when we're talking about these waves. We have transverse and we have longitudinal waves. All right, so transverse waves are waves that have particles vibrating perpendicular to the direction of the motion. All right, so that means that if the motion of the wave is going this way, right, if the motion of the wave is going this way, the particles are vibrating up and down. Right, because it goes up and down, up and down. Okay, so mechanical waves and electromagnetic waves would all be examples of transverse waves. Or how do we have? Let's talk about mechanical and electromagnetic. So, oh, I don't have the pictures. Oh. Okay, so here's transverse waves. The wave motion is going to the right, and the particle motion is going to be going up and down, because think about it as if you had like a beach ball sitting right here on the wave. The beach ball doesn't go with the wave. The beach ball just stays here and goes up and down and up and down. Right? It bobs. Okay, but the wave goes past it. Okay, so with the slinky here, a way to demonstrate that is if this hand just kind of flicks the slinky up and it just ripples through the slinky. Okay, that would be a mechanical wave. Well, electromagnetic waves are going to be ones that don't require medium, and so here you would have you have to have both a magnetic field and an electric field contained in the electromagnetic wave, and it would be traveling through, the wave would be traveling through the magnetic field and the electric field at the same time. Okay. Ocean waves, here's that ball again, right? As the waves go by, this is an example of a mechanical wave. As the waves go by, they're going this way, but the ball is just going up and down. Okay, and for those of you who think that ocean waves or water isn't something to mess, or is just whatever, and you can get around it, well, you remember that tsunami back in 2011, 2012 that hit Japan? Yeah, here's an example of what that wall of water would look like coming towards you in your house. How would you like to be in that house and see that wall of water coming towards you? That's pretty high up. I don't know about you, but I don't want that. Okay, a lot of power there. A lot of energy. All right, longitudinal waves. These are waves that have particles vibrating parallel to the direction of the motion. All right, so with a transverse wave, you're going to see this nice up and down, but with a longitudinal wave, there's no up and down. All you see is that the wave is going in this direction. Well, guess what? The particles are moving in that direction as well. Okay, so if we held this slinky on the end and we pushed it and then pulled it back, okay, we're not going to make it go up and down or side to side. We're just going to push and pull, push and pull. It's like a spring. That's a longitudinal wave. Okay, and then the matter is going in the same, or particles are vibrating in the same direction that the wave moves. All right, waves will have crests and troughs if it's a transverse wave, and it's a compression and a rarefaction if it's a longitudinal wave. Okay, so in a transverse wave, here's your trough and here's your crest. In a longitudinal wave, your rarefaction is the part that's all kind of spaced out, and the part, well, let's come back here. All right, so crest is the highest point of a wave, the highest point of a wave. The trough would be the lowest point of a wave. Okay. Compressions would be the squished areas of the longitudinal wave, squished areas right here. Okay, and rarefactions would be the spaced out areas of a longitudinal wave. Okay, so make sure that you know that compressions and rarefactions go with longitudinal, crest and trough go with transverse. All right, amplitude. Okay, so amplitude is going to be a measure of the amount of particle vibration. So it measures the number of particle vibrations. Okay, for a transverse wave, it's measured from the rest position to the crest or from the rest position to the trough. And it's expressed in SI units of meters. Okay, because we're looking for distance, so meters, little m. Okay, so here's your rest position, which is in the middle, and your amplitude would be how high up it goes from rest or how low down it goes from rest. All right, the period is a measurement of the amount of time it takes for a wave to pass a given point. Okay, it's represented by the symbol capital T, big T, and it's expressed in the SI unit of seconds. Okay, remember 1s for seconds. In this diagram, we see that this top part, the crest, goes by this young man 2 times. Right? So right here, nothing, it hasn't gone by anything yet. Okay? And here, this would be 1 second. It's moved to here. This is 2 seconds. It's now up at the top again. So the time or the period that it takes for this to travel would be 2 seconds. All right, the frequency. The frequency is a measurement of vibration rate. Okay, rate. Frequency is rate. All right, frequency is represented by the symbol, it's a lowercase f. It's typically going to be a cursive f or a slanted f or italics, and it's expressed in the SI unit of hertz. The symbol for hertz, or the unit for hertz, is Hz, symbol for hertz, and that's the same thing as 1 per second. All right, in the diagram here, we can see that it's, if the period is 2, if it takes 2 times to get through here, the frequency is 0.5 hertz, 0.5. All right, wave speed. How can you calculate the speed of a wave? Well, if you remember, speed from the previous unit is the same thing as distance over time, right? Distance over time. All right, well, here we're going to do wave speed is equal to wavelength distance, divided by period, which is time, right? So it's going to be distance over time. Yay, it's the same thing. Look at that. All right. Wave speed, if we wanted to do wave speed in another way, we could also say that it's equal to the frequency times the wavelength. So here we would have frequency times the wavelength. And I'm writing this in cursive because it's easier. It might not be prettier, but it's easier. All right, so frequency times the wavelength. Okay. All right, the speed of a wave depends on the medium that it's traveling through. So in general, wave speed is going to be faster or greatest in solids and less or least in gases. Well, why do you think that's possible? Okay, think about the wave is transferred as a vibration from one atom to the next. And we talked about solids, liquids, and gases. Which one's going to have the atoms are touching? Well, it's going to be the solids. The atoms are close and compact, not toast. Although toast is a solid, right? So the atoms are close and compact, whereas in a gas, they are all spread out. So it's not going to transfer the energy, and waves are energy. So gases won't transfer them as easily and quickly. All right, in a given medium, the speed of the waves is constant. It stays the same all the time. Okay, in a given medium, the speed of the wave should remain constant. All right, kinetic theory is something that explains the difference in the wave speeds. And kinetic theory just pretty much says that if a molecule is heated, it's going to speed up and it's going to get faster. And if a molecule is cooled down, it's going to slow down, and the vibrations will slow down some, so it's not going to be able to transfer things as quickly. All right, so light is one of those weird things that light is a wave. Okay, light waves, light speed, and it has a finite speed. Okay, it has a finite speed, a definite speed. It doesn't change. Okay, so the speed of light with a little c, that's the symbol for the speed of light, is 3.00 times 10 to the 8th meters per second. Okay, so the speed of light in a vacuum is 3.00 times 10 to the 8th meters per second. Okay, for electromagnetic waves, if we were to figure out what the speed of electromagnetic waves would be, we would set it equal to c, and we would say that it's the frequency times the wavelength would be equal to c, and that's how they figured out the speed of light. Okay, because visible light, what we see is actually an electromagnetic wave. Yes, it is. All right, so if we wanted to find the speed of light, we just take the frequency times the wavelength, and there you go, 3.00 times 10 to the 8th, right? Okay, relationship to energy. Amplitude and frequency tell you about energy. Okay, the larger the amplitude, the more energy there is. Less frequent, or nope, sorry, the higher the frequency, the higher the energy. Okay, more amplitude, more energy, higher frequency, higher energy. All right, so let's do an example. The string of a piano that produces the note middle C vibrates with a frequency of 262 hertz. If the sound waves produced by this string have a wavelength in the air of 1.30, and I'm going to use little lambda as wavelength, what is the speed of the sound waves? Well, if you remember that the velocity of a speed, or the speed of a wave, is equal to the frequency times the wavelength. Okay, so we have frequency, we have wavelength, we just have to plug those in. So 262 hertz, and we multiply that by 1.30 meters, and we should end up with 262 meters per second. Sorry, I copied the wrong number. 341 meters per second. All right, real quick. Doppler effect. As an ambulance comes near, the pitch of the ambulance changes. Okay, well, why does it change? Well, the pitch of a sound, high or low, is determined by the frequency at which the sound strikes your ears. Okay, a higher pitched sound is caused by sound waves of higher frequency. Okay, and then the frequency changes when the source of the waves is moving towards you. Okay, and we'll talk about this in class. And here's a little Big Bang Theory for you that tells you that the Doppler effect. All right, have a good day.